great honor to be today with you. I am afraid I will speak about things which are rather far away from what are you doing here. But I do hope that perhaps one day we theoreticians could produce some concrete predictions which could be eventually checked and tested in the real universe. So my topic today is the origin of space and time, and in fact of matter in the non-commutative universe. First, I will introduce the non-commutative methods because they are less known to you perhaps, and then in the second part of my talk I will present some results obtained by my group. It will be a simple Friedman cosmological model, which will be viewed in terms of non-commutative geometry. To give you some idea of what we are talking about, let us look at that slide here. Let's imagine that we are here in the macroscopic world, and our task is go to the beginning of the universe, or perhaps better, to the most fundamental level of physics, which, as you know very well, it's called Planck level. And there are two ways along which we can go to the Planck level. The one is the astrophysical way, when we go backward in time in the universe and we try to reach its beginning. When we go back, oh, I am not accustomed to that thing. Okay, when we go backward in time, the universe shrinks, contracts, and the density is bigger and bigger, and finally when we reach this density, 10 to 93 gram per centimeter cube, we are already at the Planck level, the most fundamental physical level. But there is another way of reaching the Planck level. It is now, not backward in time, but now deeper and deeper into the space. This is the way which is pursued by theoretical physicists when they try to reach higher and higher energies and probe smaller and smaller distances. They are approaching the Planck level, and if one day we reach large enough energies so that we would be able to probe the distances 10 to minus 33 centimeters, then we will be again at the Planck level. So let's notice that here we are at the Planck level backward in time, and here now, but deeper into the space. But there are no two Planck levels. It is just the same single Planck level. This says us something about the nature of the Planck level. It says that Planck level is non-local, because almost 14 billion years ago, and this is now, and we reach exactly the same, so to speak, physical structure. So this tells us that most probably Planck level is non-local. And this is why we are using non-commutative geometry, because non-commutative geometry is geometry, but it's totally non-local, as we will see in a moment. That's a nuisance. It is that way. That would be simpler. Okay. As you know very well, there are several, or at least few, various methods to reach Planck level. The superstring theory and its the most recent incarnation, which we called M theory, the loop quantum gravity, causal dynamic triangulation, quantum group approach, and non-commutative geometries. These two, the latter two, are in fact the same, because quantum groups are symmetries of non-commutative spaces. I shall not speak about all these approaches, but I will only dwell on that one. And my talk is based on these references. These are my friends, my co-workers, Dr. Pysiak, Dr. Sasin. This paper here gives mathematical details of our model, printed in Journal of Mathematical Physics. This one, the second one, Journal of Theoretical Physics, is physical aspect of the model, and these two papers concern Friedman cosmological model. It is computed in terms of non-commutative geometry. First, I will try to explain you main idea of non-commutative geometry. So let us start with commutative geometry. As you know very well, geometry of space-time, this line here, the top line, represents space-time, M. As you know very well, the standard geometry of space-time is done in terms of coordinates. But there is another equivalent way of doing the same thing, namely in terms of smooth functions defined on M. Here we have some graphs of few functions, and all such functions, all functions which are smooth on a manifold of space-type manifold, are denoted by C infinity M, and they form the algebra. They form algebra. This means that the function could be added, could be multiplied by scalars, and multiplied with each other. So we can do standard geometry of space-time in terms of coordinates, or equivalently in terms of the algebra of smooth functions on the space-time manifold. The second way of doing that in terms of the algebra is perhaps less practical. It's more sophisticated, but it is better as far as generalizations of the standard geometry are concerned. So we will be doing now geometry in terms of the algebra of smooth functions on M. How to recover points in terms of the algebra. Here we have a point P, and it's obvious that all functions belonging to the algebra C infinity which vanish at that point, they determine that point. So we can regard point P, or equivalently all functions will vanish at that point. All functions of the algebra C infinity of M which vanish at P form a structure which in algebra is called maximal ideal of this algebra. So this is maximal ideal of the algebra. Of course, maximal ideals can be defined without any references to points, and point can be identified algebraically with ideals of a given geometry. And now we will go to non-commutative geometry. The idea is very similar. The capital A denotes any non-commutative algebra, and non-commutative means that if we have two elements of such an algebra, A and B, then if you multiply first A and then B, it is not the same as B multiplied by A. For instance, you can think about the algebra of matrices. The multiplication of matrices is non-commutative, and matrices can define a non-commutative geometry. It's a nice story about Alain Kohn, who was one of the greater inventors of non-commutative geometry. He was once approached by a French TV journalist who asked him, please explain us in a very simple manner, what does it mean, non-commutativity? And he said, okay, it's not very difficult. If you have a multiplication table, and if you multiply 3 times 7, it is the same as 7 times 3. And then the journalist objected, no, it's not the same. And then Kohn was struck by this fact. And how is it not the same? Because 3 times 7 is more difficult than 7 times 3. So in this respect, it was not commutative, but as far as ordinary multiplication is concerned, it is multiplicative. It is commutative. Okay. And now, if we do geometry exactly in the same way as in a commutative case, but instead of the algebra C infinity, we take any non-commutative algebra, and we proceed exactly in the same way. This will be non-commutative geometry. But the difference is enormous, because in non-commutative geometry, in general, there are no maximal ideals, so there are no points. Some people call non-commutative geometry pointless geometry with no point. And some malicious people say that indeed it's pointless, without meaning. Okay. So since there are no points, the functions, so to speak, have no support. And this is why non-commutative spaces are sometimes called virtual spaces. So in fact, we are dealing with the algebra, and we suppose that some space is underlying this algebra. So the strategy is similar to the strategy which was once used when complex numbers were invented. People say, well, there is no square root from -1, but let's just suppose that there is one. So we are doing the same in non-commutative geometry. Non-commutative algebras have no support, but let's just suppose that they have some. And this is called, this support is called non-commutative space. If you don't like, some people don't like the idea of non-commutative spaces, you can forget about spaces and simply do corresponding algebra. Well, if we adopt non-commutative geometry, well, to model the universe, of course, our macroscopic universe is a commutative one. But if we go to the Planck level, we could expect some sort of non-commutativity. And if we do that, then the consequence of that fact is the following, that on non-commutative regime, on the non-commutative level, there will be no time, because time is composed of moments, instances. And if there are no points, no instances, there is no time. There is no space in the usual sense. And there are no other local concepts. Only global concepts are important, are valid in non-commutative geometry. Well, what about dynamics? Because dynamics is something which changes in time. Well, happily enough, dynamics can be defined in non-commutative regime. Namely, you can always define dynamics in terms of vectors. A vector is a velocity vector or momentum vector. And of course, there is no concept of vector in non-commutative regime. But there is a counterpart of the concept of vector field, which is not local thing. And you can define dynamics in terms of the counterpart of concept of the field. This counterpart is called derivation of the given algebra. And now I proceed to present some fundamentals of our model, which we have proposed, a cosmological model. Let us start from that part of the picture. Here is again the space-time M, the event in space-time X, and we will consider something which is very, very well known in mathematical physics, the fiber bundle of reference frames on this, over the space-time M. What is the fiber bundle of reference frame? It is simply the set of all possible local reference frames in space-time. The local reference frames are 4 orthogonal vectors, local reference frame. And here, the local reference frame is represented by this point P. So they are 4 linearly independent vectors. And this local reference frame is attached to the point X. This is a natural projection from the space E, the space of all local reference frames. This space E is called total space of the frame bundle. and this frame is attached to the point X. This line here represents a Lorentz group. So if we act on this of this reference frame with the element of Lorentz group, this means we rotate this reference frame, we obtain another reference frame denoted here by PG. G is an element of the group of the Lorentz group which rotates that frame, and this is frame already rotated also over the same point. And this is called fiber over X. And this space E is composed of all fibers over space-time. So this is very well-known construction in differential geometry. But in order to change to non-commutative geometry, there is a standard method. And this standard method is presented in that part of the picture. Here we have the space-time M. This is the fiber bundle, this space E here. But we multiply this space E in the Cartesian way by, again, the same structural group, Lorentz group. And we denote this Cartesian product by gamma, capital gamma. And it has a structure of what in mathematics is called groupoid. The concept of groupoid is a generalization of the concept of group. As you know, group are used in physics to describe symmetries. But the groupoid is a generalization of the concept of the group. There are some physical symmetries which cannot be described with the help of groups. For instance, quasicrystals. But quasicrystals have symmetries which can be described by groupoids. I shall not go into the detail of groupoid structure. It is enough for us to remember that this space gamma is a groupoid, and these elements of this space are pairs, of course. P is element of E, and G, element of the Lorentz group, is element of G capital. So element of this gamma, of groupoid, are pairs, which I'll denote here by gamma. And such an element of the groupoid can be represented as an arrow from P to P times G. And this arrow represents Lorentz rotation from the reference frame pre-P to this reference frame. So the groupoid, in fact, is the space of all possible Lorentz rotations. It's something very, very physical, because Lorentz rotations are something very important for physics, and our phase space of our model is the space of all possible Lorentz rotations. Okay? And now we construct the algebra, non-commutative algebra, over this groupoid, which is called sometimes transformation groupoid. And this algebra is here. This algebra E, they are smooth functions. Smooth means this infinity denotes smooth. Compactly supported, so the compact space are supports of compact sets are supports of these functions, and these functions are defined on this groupoid gamma, and they are values of these functions are in complex numbers. So they are complex valued, compactly supported smooth functions, and of course it is, since functions are always multiplied in the standard way, it is a commutative algebra. In order to make it non-commutative, we change the rule of multiplication. And the new multiplication is here. It is also very well-known mathematical operation, which is called convolution of two functions. The function f1 and convoluted with the function f2. These functions are elements of this algebra, are defined with the help of this integral here. As you see, this integral suggests that it is a non-local operation, because you must integrate over the entire space of some part of that space. I shall not go into the mathematical details of these operations. This is what we call outer center of this algebra. It is important in mathematical structure of the model, but I shall skip that problem. It's more technical. And now our idea is to construct differential geometry in terms of this new non-commutative algebra. I mentioned a while ago the concept of generalized vector fields. Such a general vector fields are called derivations of a given algebra. And in our case, there are three kinds of these generalized vector fields, derivations. There are horizontal derivations, vertical, and inner. I will not go into the details of that, but into account the fact that these two derivations, vertical and horizontal, will define our gravitational sector. That means generalized general relativity. And the derivations, inner derivations, will define a quantum sector. Such a pair, where here we have an algebra, a non-commutative algebra, and some set of derivations, such a pair is called differential algebra, because with the help of it we can develop differential geometry. That means metric, curvature, space, Riemann tensor, and everything. And now I will apply this non-commutative space machinery to describe closed Friedman universe. And this is not very difficult. It is simply an application of the general scheme to closed Friedman model. We have here space-time is described by four coordinates, standard coordinates. Eta coordinates means time, and time goes from 0 to t. 0 is the initial singularity, and t is final singularity. Here, singularities are not included into the description of the model. They can be included, but it's another story. And we are considering a closed Friedman model. That is to say that these three space coordinates are on the three-dimensional sphere. So the model is a Cartesian product by time and a closed spherical space. The metric on such a space-time is a standard metric from every textbook of general relativity or cosmology. This is the form of the metric. And this is very well known and standard. And now we try to construct everything according to the previous scheme. So the first point is to construct the space E, capital E, which is a total space of the fiber bundle of reference frames. The Lorentz group, which is a structural group of this frame, is here. And we have chosen a very simple sub-group of a Lorentz group. It describes boosts, very well-known boosts in general relativity. And this is a very convenient here because we have here only one variable t. So everything depends on one variable here. And owing to this fact, the fiber bundle space has the same four coordinates like space-time, and plus one more coordinate, lambda, which is in this case lambda belongs to R. So this is the space of the fiber bundle. Normally, fiber bundle has 10 dimensions. Space-time has 4 dimensions, fiber bundle 10. But owing to this simplification that we have restricted to that subgroup, it is only 5 dimensions. And now we construct gamma, the groupoid gamma. Groupoid gamma has 4 space-time coordinates and 2 coordinates, because gamma are in fact pairs, as we have seen. So there are 2 numbers belonging to R. So gamma is also rather a simple space. And then having gamma, we define the algebra of compactly supported smooth functions with values with complex numbers. And the convolution, the multiplication, is defined here. if you look carefully at this formula, it is rather transparent. The first coordinates are here and here. You add here there are two reference frames, lambda 1, lambda 2, this lambda 1, lambda 2, and here is another lambda, which is a variable of integration. And now we define metric on that groupoid by using vector fields horizontal and vertical, and the metric is here. And having this metric, we do automatic computations of all tensors and magnitudes needed to write Einstein equations. And this can be done with the help of Mathematica problem in a couple of seconds. I skip all these intermediary computations, but only the Einstein operator. If you remember, Einstein equations have left-hand side and right-hand side. Left-hand side is geometry, right-hand side is distribution of matter in space-time. And left-hand side, it's called Einstein tensor. And if we use Einstein tensor with one index up and one index down, it is operator. This operator is given here. This matrix, 5 times 5 metric, and B, H, and Q are here. Just computed with the help of Mathematica. And here are Einstein equations. And now we have made one additional investment. We have changed a little bit Einstein equations. In our case, Einstein equations have the form of the eigenvalue equation for Einstein operator. So it is similar like in quantum mechanics. This is Einstein operator, and this is eigenvalue equation. So there are vectors, the vector fields, derivations, and this tau is generalized eigenvalues. Generalized because usually eigenvalues are scalars, and in our case they are functions. Very important thing here is that there is no matter here. There is no energy momentum tensor in this equation. They are purely geometric equation. Einstein operator and its eigenvalue equation. And this equation has such a form. And now our task is to solve that equation. This can be done almost immediately. And the solutions, the generalized eigenvalues, are the following: tau B, tau H, and tau Q. They solve this equation, like usually in mathematics when we try to solve eigenvalue equation. But now something very nice happens. If we compare these eigenvalues here, if we compare them with standard Einstein equations for closed Friedman-Wurth model, then we find this out, that in fact the magnitudes tau B and tau H are related to the components of the energy momentum tensor. So there was no energy momentum tensor, but it turns out that matter components were somehow encoded in the generalized eigenvalues of the Einstein equation, Einstein tensor. So if we denote this ratio here by T11, so TOO, so this is the 0,0 component of energy momentum tensor, is minus tau B divided by G is gravitational constant. we assume that, for simplicity, that the velocity of light is 1. So this is time component of energy momentum tensor, and these are the remaining components are related to pressures, and these two, like that. In this way, we obtain components of the energy momentum tensor as generalized eigenvalues of Einstein operator. We think that is a very nice circumstance, because at the beginning there was no matter at the Planck level, purely geometric quantity, and then by comparing with macroscopic Friedmann-Wells model, it turns out that some magnitudes are related to matter. But as we remember, there were 3 eigenvalues, generalized eigenvalues. Tau B, tau H, and tau Q here. So these correspond to density and to pressure in the components of the energy momentum tensors. This magnitude dependent of the remaining ones, and it satisfies this equation. So it is a relation between density and pressure. And as we know, the relation between density and pressure is the equation of state. So again, the equation of state was not assumed here, but it's somehow reproduced by this machinery. And if we put, if we put TQ equal to that magnitude, we obtain the equation, state equation for dust, and if TQ is 0, we have radiation. So this equation is a constraint of all possible state equations. Every state equation we can imagine must satisfy this equation here. And all known equations of states, they really do satisfy it. Well, this was a gravity sector of our model, and I have no time to present its quantum sector, but very quick, some interesting results. Quantum sector is obtained in this way. We have the algebra the formula which determines this representation. What is extremely nice, and again it was not put by hand in our model, but came out of the model, and I must say we were very nicely surprised when it came out. Namely, every operator, every element of the algebra A, every element of this algebra generates a random operator. This quantity here, the family of coming from this representation, is a random operator on this family of Hilbert spaces. So some probabilistic aspect came out of the model. And this is a definition, what we do mean by random operator. I shall not go into details of that definition because it's rather technical. Well, we know what does it mean, randomness. And this randomness is a little bit generalized, well, usually. The point is that if we are regarding only gravitational sector of our model, there is no randomness in it. But if we go to quantum sector, the randomness appears. So probability aspect of the model comes out. And now, something referring to the title of my talk, Emergence of Space-Time. So at the Planck level, when we have a non-commutative regime, there is no space, no time, because everything is no local. But of course, we must recover somehow space and time. And this is done in the following way. To go from non-commutative regime to the usual space-time geometry, we must somehow to make the algebra a-commutative. And there is a very nice way of doing that. We must, in a suitable manner, averaging elements of this algebra. So if we have A is an element of the algebra, this is some technicality. If A is an element of the algebra A, this integral means averaging of that element. And averaging kills non-commutativity, and we obtain the standard geometry, standard algebra of smooth functions or manifold, and we recover all macroscopic structure. I have some 5 minutes more, and I want to finish that with also something which I think is remarkable in that model. It's a sort of summary plus one new ingredient. Our non-commutative closed Friedman world model is a toy model. We do not pretend that it is a correct one. It's based on many simplifications, and non-commutative geometry is not yet mature enough to present non-simplified model. So it is a toy model. It is intended to show how concepts can interact with each other in the framework of non-commutative geometry, rather than to study the real world. And we have seen that some interesting concepts beautifully interacted with each other, probability and non-locality and so on. We have seen that interaction between pre-geometry and matter is a very striking thing in our model. This non-commutative regime sometimes is called pre-geometric regime, because it's not yet space and time in the usual sense. And we saw how matter emerges and together with standard space and time. Another interesting aspect of that model, which I had no opportunity to present here, but I will now mention only, is the interaction between what is singular and non-singular. It's an old, difficult problem of how to avoid the initial and final singularities in cosmology. And here we have some interesting possibilities. Usually, two possibilities are considered. Either the future quantum gravity theory will remove singularities or not. And usually people hope that the first possibility would be implemented, that future quantum gravity theory will remove singularities. Although, strictly speaking, it's not that clear. Some models now remove singularity, some quantum models, and some do not. A quantum sector of our model, which was not explored fully in this talk, as we saw, has strong probabilistic properties. All quantum operators are random operators in our model, and they form what is called in mathematics von Neumann algebra. Because of this, the fundamental level, the Planck level, is probabilistic level. And from the probabilistic point of view, it turns out that singularities, they are over there. They are not removed, but they are probabilistically irrelevant. They form the set of measure zero in the set of all the other possibilities. And if we write the dynamic equations of our model on that level, which can be done, we, with our eyes, can see that dynamics goes through singularities with any trouble, because they are zero set model, and everything is probabilistic, so everything is modular zero set models. But only when we go from the non-commutative regime to the macroscopic physics, then this process can also be studied in detail. Then space appears, time appears, matter appears, and also singularities became more significant. But we can say that they are only some effects of our simplifications, of the fact that macroscopic physics is only an approximation to what is going on the fundamental level. So the problem of singularity in the interior of black holes is not yet solved, but at least we have another possibility. Perhaps they are probabilistically irrelevant. Thank you.
Are there any questions or comments?
Actually, the obvious question is, how do you think that these theories can be tested? How can we know that this is right or wrong?
Well, we share the same fate with other approaches to quantized gravity, that we are looking for some observational tests, but for the time being it is not that easy. But nevertheless, some things can be said about that. Namely, perhaps there are two comments on that. The first comment is the following. When you do fully quantum sector of our model, we have dynamical equations, which are a bit different equations because there is no time, but there is a parameter which behaves like a sort of time, and with respect to that parameter, the dynamics can be written down. And of course, these equations are no local. So if they predict some effects, they are non-local effects. So there will be effects consisting on correlations among distant events in the universe, which is also nice because, as you know, in quantum mechanics, there are indeed non-local events, and they are, I think, beautifully explained with the help of that model. This is the first thing, the first remark. The second is the following. When in the formalism of our model we try to make a measurement, a concrete measurement, the measurement is done in the macroscopic space. Always the apparatus is located at the point X in the manifold. And it turns out that if you write the equations for the measurement, these dynamical equations in quantum regime, and then you applied measuring apparatus, then all this non-local machinery collapses to that point P or X in which your apparatus is located. And all this machinery, all this non-commutative model collapses to the standard formalism of quantum mechanics. So in the view of this model, quantum mechanics is nothing else but the theory of measurement within that model. So this is partial answer or comment to your question.
How would be this related to the instant in which the universe starts to exist? Or what do you feel about that?
Perhaps the comment or answer, the answer is I don't know, but I can comment on that. The comment is the following, that time is a macroscopic concept. So in our model at the fundamental level there is no time. There is only some pre-geometric, well, non-commutative something. And it might be, at least from the point of view of our model, because I don't pretend that it describes this concrete reality, but in our model there is no beginning and no end. When the concept of beginning and end are products of the fact that we are making physics from the point of view of macroscopic magnitudes. So at the fundamental level there is no time and no space, so the concept of the beginning is probably meaningless. It becomes meaningful only when we ask this question from the perspective of the macroscopic physics. I know that it is very difficult because when we came to these conclusions very slowly, in fact, it's like several years, because it's very difficult to change your thought categories from what we are accustomed to something which is completely different. But the only way of doing that is to forget about your intuitions connected with space, time, matter, and just follow very strictly mathematical formula. Interpret them even if they say something which is repugnant to you. But this was always in physics like that.
Yes, but why do we see something like an origin from our perspective? What is the problem?
Because when we have the formalism of our model, and there is no beginning, but if we make a transition from non-commutativity to commutativity, then time appears, and it turns out that this time is not extending to minus infinity, but has some limited instance. So it is simply a result of formalism, of a formalism.